Hello everybody, you're very welcome to this episode of Programming and Algorithms. In this episode we're going to look at recursion, and in particular we're going to look at recursive programming. We've already seen roughly what recursion means in terms of a data structure. So we saw that a node of a linked list is made up of a value and a pointer to a node of a linked list. Therefore the value is separate, but the node is contained within itself. And recursion simply means that any time you have an entity that contains that entity within itself as well. So, for example, this picture has the picture in it, and in it, and in it, and in it, all the way down. Or Russian dolls is a good example, because the Russian doll has a Russian doll inside itself. So in programming terms, we can create a recursive program. What that means is we create a module, and then in the middle of that module, we call that module. What that allows us to do is, if we've got a complicated problem, break it down, keep breaking it down, keep breaking it down, until we've broken the problem down into something very simple. We solve the very simple problem, and then the bringing together of all of the steps we took to break it down will solve the overall problem. Recursion, and specifically recursive programming, allows us to do this because the computer will allow us to call a module or method within itself. Let's think about our factorial example we did before. We know that 7 factorial is 7 by 6 by 5 by 4 by 3 by 2 by 1. And we know that 6 factorial is 6 by 5 by 4 by 3 by 2 by 1. Therefore, what we can say is 7 factorial is 7 multiplied by 6 by 5 by 4 by 3 by 2 by 1, which is 6 factorial. So 7 factorial is 7 multiplied by 6 factorial. 9 factorial is 9 multiplied by 8 factorial. And n factorial is n multiplied by n minus 1 factorial. Or if we want to call it like a module or method, we'd say factorial n is equal to n multiplied by factorial n minus 1. Let's remember how we did factorial iteratively. So iteratively we have a total, we read in a value, we keep looping around multiplying that value by total, which starts as 1. We keep decrementing the value, so we do the number of multiplications necessary until we get to 1. And then we've got our factorial, so that's iteratively, or using a loop. Now let's look at it by implementing factorial n is equal to n by factorial n minus 1. So we have a module called fact, and fact takes in a parameter n. As long as if n gets to 0, then we return the number 1, else we return n by fact n minus 1. So takes in fact n, and then says as long as the number passed in isn't 0 or less, we just multiply it by, we take that number, multiply it by the fact of n minus 1. So let's say the number is 4. What'll that tell us? That'll tell us it's fact 4 is 4 multiplied by fact 3. And fact 3 is 3 multiplied by fact 2. Fact 2 is 2 multiplied by fact 1. Fact 1 is 1 multiplied by fact 0. And what's fact 0? It's 1. So we get 1 by 2 by 3 by 4. And we can call it by having our program called Factorial that says get a value from the user, print out the fact of that value, which we'll call our module. So within the definition of the module fact, we have the module itself being called. If n is 5, fact 5 returns 5 by fact 4, fact 4 is 4 by fact 3, fact 3 is 3 by fact 2, fact 2 is 2 by fact 1, fact 1 is 1 by fact 0, which is 1, so the whole thing works out as 5 by 4 by 3 by 2 by 1, which is 120, which is correct. Let's think about the Fibonacci number sequence. So remember we did it iteratively by declaring two numbers, first num and second num. and then we had a total that was the sum of those, and then first num became second num, and total became second num, and away it went. That's iteratively. Now the recursive version is quite simple. It just says fib in is fib in minus 1 plus fib in minus 2. So if the first Fibonacci number is 1, the second Fibonacci number is also 1, the third is 2, the fourth is 3, the fifth is 5, the sixth is 8, and so on. So if I type in fib 2, it's the number 1 still, because it's 1, 1, 2, 3, 5, 8, etc. So my check here is, if n is 1 or 2, then we return 1, otherwise we return the fib of n minus 1 plus n minus 2, and that will give us the Fibonacci number value at a given position for n. How do we convert decimal numbers into binary? Well, if we have the number 23, we'll recall, we keep dividing it by 2 and look at the remainder. 23 divided by 2 is 11, remainder 1. 11 divided by 2 is 5, remainder 1. 5 divided by 2 is 2, remainder 1. 2 divided by 2 is 1, but remainder 0. 1 divided by 2 is 0, and remainder 1. So the decimal of 23, if we read those remainders up, it's 10111. If we want to write a program to do that, if we want to write a program to convert a number into a binary string, how we do it is we'd say, if the number put in is 0, then return the string value 0, else return this same program again, dividing, and this is integer division, n by 2. So let's say it's 11 the first time, then 5, then 2, then 1, and the string value of n mod, that is the remainder of 2. So we're going to get the string part adding on the values successively each time until we reach 0, and then the string value 0 will be added on. So that's our decimal to binary conversion. We said it already that a linked list is a recursive data structure because the pointer points to a node. A node is made up of a value and pointer, and the pointer points to another node. So it's kind of natural that we could use recursive modules to manipulate linked lists. So we could look at the modules we had in the linked list section and look at how we might recursively implement those as opposed to iteratively. If we want to count all the values of the linked list, there's a simple way of counting them. We just count the first value, and then we say, and whatever the rest of the length of the list is. And how do we determine the rest of the length of the list? Well, we look at the first value in the rest of the list, and first value is 1 plus the rest of the list, and the rest of that list is 1 plus the rest of that list, and the rest of that list is 1 plus the rest of that list, until we get down to just one value, and then it's 1 plus 1 plus 1 plus 1 plus 1. So that's our recursive count. Simple. Recursive count is if we're pointing to the null, then we return 0, else we return 1 plus recursively counting the rest of the list, which is current.pointer. How do we recursively print out all the values in the list? It's the same kind of thing. If the current pointer is pointing to null, then we don't print out anything, else we print out the current value, and then we recursively print the rest of the list. So print out the current value and then print out the rest of the list. Simple as that. How do we find a node recursively in a linked list? We find a node simply by checking if what we're pointing to at the moment is null. If it is null, then return null. Otherwise, what we say is, if the value we're looking for is the current value, then we print out we've found it, else we return this module again, find a node, not with current though, but with what current is pointing to, and n, So we'll keep calling find a node with the next value until we find the current value equal to n, and then we'll print out n was found. How do we insert a node recursively? Inserting a node is quite simple. With a pointer, with what position we want to insert it in and what value. And if by any chance the current pointer is pointing to null, then we'll return we've reached the end of the list. Otherwise, if we've found the value we're looking for, then we create a new node, and now the new node pointer points to whatever current points to, and current pointer points to the new node. So if we found it, we do that. Else what we do is we just keep calling that, not with current though, with current.pointer, so we traverse the whole list. How do we delete a node? Deleting a node is a dottle. It takes in the current pointer and n. If the current pointer is null, then we can't delete that node. If it's not null, then if the value we're trying to delete, n, is found, it's the current one, then we just say now current points to whatever current.pointer is pointing to. Otherwise, if we haven't found it yet, current.pointer gets reassigned to point to delete a node, the next element of this current pointer and n. So we're going to recursively traverse the list, moving along current pointer, and if we find the value we're looking for, then we just skip over it by saying current now points to whatever current is pointing to. So thanks very much, that's recursion.